All right, it's cooking. All right, so tell me, Prim's algorithm. Now that we've covered communism and dumb athletes. Not all athletes are dumb. We have a couple athletes in here who are relatively intelligent and a couple who aren't. What, football?
Lacrosse.
Oh, lacrosse, that's right. He's actually quite intelligent. He just is probably more into lacrosse than he is to academics. It has nothing to do with ability. It has everything to do with priority. So tell me about Prim's algorithm.
It's greedy.
It's okay. It's a greedy algorithm. Tell me about that. What does that mean? Since you researched it and have been whining about it.
Well, I know it has to do with, well, the greedy part doesn't, but Prim's algorithm has to do with minimum spanning tree.
Okay. By the way, you're on the hiking team, right? The guy who doesn't like the outdoors.
I actually took my gym credit was hiking, and it was the greatest day ever because it's supposed to be a one-day class, except it rained. So we hiked for half an hour, and then the professor decided we were done. So we
Well, you were out in the rain?
Yeah, it was terrible. And it was after a lot, so I had no sleep. I was just done with it.
All right, so you said it's a greedy algorithm. Tell me what it means to be a greedy algorithm. Then you started babbling about spanning trees, but give me the... So in general, what does it mean to be greedy? So remember, this course is kind of split into two pieces. One piece is data structures, which we've done a lot of. And now we're starting to do some of the algorithm stuff and thinking about that side. Well, so before I even answer that, what's an algorithm? And I'll swing over to you next.
It's like a set of steps to solve a problem.
Okay.
Or a sequence of stuff in order to get something.
Fair enough. So when we say algorithms big A, let's say, we're really kind of talking about researched, famous algorithms for solving complex problems. We've talked about time complexity at various points where certain problems kind of fake us into thinking that they're going to be efficient, but in the end, they actually are mathematically quite inefficient. I think we saw that with the fractions problem, right? When we're adding fractions, it's like, oh my gosh, reducing a fraction, which seems pretty trivial, is actually ridiculously complex from a time perspective. And it's easy for us as, first of all, as humans, where we have this, we're in kind of a state of awe about how fast our computers are. And generally speaking, we can write pretty inefficient algorithms for most problems and not notice the difference because our computers are so fast. But every now and then we stumble upon something, I guess, mathematically, sufficiently mathematically complex that our horsepower doesn't help. So when something is a greedy algorithm, that kind of speaks to its nature. What does it mean to be greedy? What does it mean to be greedy in real life?
You want to keep everything to yourself. You want everybody else's stuff.
Okay, we don't worry about everything else. We don't worry about resources. We don't worry about CPU time. We just grab and move, right? So a greedy algorithm would constantly, and in this case what it does is it's saying, okay, I'm going to take all possible paths. Okay? I don't care how much extra time that takes. I'm going to take all possible paths and then compare them in the end. I'm purposely going to do a brute force attack on this thing and figure out how to handle it. What were we going to say?
It looks at all the edge weights between each vertex and takes the one that has the smallest value.
Okay, what does that mean? Is it a memorized sentence or is that
From what I understand of it, there's one vertex you start at randomly, and then
one vertex of what?
Okay.
What kind of animal are we dealing with here?
Any kind of value.
Okay, any kind of value. You said a graph? Weighted graph. Okay, so we're dealing with a graph. What's a graph?
Collection of values.
Okay, so basically it looks kind of like a tree, like a blob of nodes that are all hooked to each other in some way, right? So could we say it's kind of a tree that doesn't have a defined starting point? Is that kind of a graph? All right, and then you mentioned this is an undirected graph, right? Okay, what does an undirected graph mean?
It doesn't really have a set style or path,
Yeah, every edge, as you pointed out, is a two-way street. Okay, if we think about each node as being a city, that's kind of where I'm segueing here with this traveling salesman problem. Have we all heard of this before? at least in passing, at least we maybe don't know what it is. It's either traveling salesman problem, sometimes it's just referred to as the TSP problem. But let's imagine each node is a city. Let's say here in Wisconsin, and we have Interstate 43. Interstate 43 is two-way, right? We can go north, we can go south on that road. So that would be undirectional. All right, we can go either direction across an edge to traverse from one node to another. All right, so it's undirectional. What does it mean to be weighted?
They each have a certain weight to them. So like distance in between two cities.
Absolutely, just like distance between the two cities. So if I'm taking 43 from Mequon to Grafton, that would have a weight of 8. Let's say 8 miles-ish, or whatever it is. So, you know, that would be a weight for that edge between those two cities. Okay, so now you were saying something about when you pick a starting point, you're going to find all edges. Tell me more about that.
You're going to find like all different possibilities the place could go. So say you're starting at A, you're going to look at B, C, and D.
Assuming those are all connected to A.
Yeah.
Okay, yep.
And then it's going to take the one that has the least connection weight and then go from there.
Okay.
Look back at the next possible paths, all of them. So A, it could look, say it goes A to B, it's going to look at connections from B and back at A, and whichever one has the smallest weight is going to go that one.
Okay. So if the idea is that I'm here in Mequon and I ultimately want to get to Green Bay, let's say. So we're going to say that's more than one hop away. My starting point, let's say that that Mequon connects to 3 towns. We connect to Grafton, we connect to Cedarburg, and we connect to Germantown. Keep it simple like that. All right, we're going to take the shortest first path, right? So the shortest first path is, well, it's not going to be Germantown. It'll probably either be Cedarburg or Grafton as my guess is Grafton from a weight perspective. So we'll take Grafton first because that's the shortest path that leads from Mequon in our graph. All right, so if we kind of draw this graph here in preparation for our, all right, so that's Mequon. This is Grafton. That's Germantown. And that's Cedarburg. For giving these more legitimate distances, it might look kind of like that. And all of these guys have edges between them in this particular case. So we can go from Grafton to Mequon or Mequon to Grafton, so unidirectional. Or undirectional, bidirectional. Mequon to Cedarburg. Mequon to Germantown. All right, and then each one of these guys is going to have a value associated with it. So this might be 8. This might be 12. This might be 16, something like that. All right. So the Prim's algorithm would say, and ultimately, let's just kind of plot this out. We're going to Green Bay. All right, so maybe Grafton to Green Bay. Looks like this. Cedarburg gets to Green Bay through Grafton. Germantown gets to Cedarburg, well, gets to Green Bay through Cedarburg, which gets there to by Grafton. Let's just leave it like that. So, is this a graph? We could give some values of our weights. So, well, that's kind of a. We're actually going to Sheboygan. All right, so we're going to say this is 28, and obviously this is to scale. This is 5. And let's say this is 10. Something like that. All right. So this is a graph, right? But nothing says that we have to start in an individual place. We happen to be using our example from Mequon. But Prim's algorithm says to start at all possible points, right? And generate a bunch of what are called spanning trees. Okay, what's a spanning tree? We're ultimately searching for the minimum spanning tree, but what is a spanning tree? If you had to define that. Go ahead.
Would it be like a group of directions in order to get through them, like you say,
Okay.
would that be it?
Are you asking me or telling me?
Oh. That was my guess based on my thinking through.
Well, first of all, a spanning tree would likely be a tree.
Well, yeah, like.
All right, so it'll be a tree, and it'll be a tree. What properties does a spanning tree have? Okay, so it meets all locations, or at least all locations we're interested in. Okay, and this is going to kind of get us back to this whole traveling salesman problem. All right, so a spanning tree on this graph, if we said we were interested in all of these cities, would be a tree that visits each one of these cities. It includes every single one of them. The minimum spanning tree would be the tree that has the lowest cumulative weight. We add up all these edges while still visiting every city. That makes sense? All right, so Prim's algorithm is an algorithm for finding a minimum spanning tree which visits every single node in a undirected weighted graph. Is that a fair assessment? Does that sound kind of like what you read? All right, so traveling salesman problem is a common problem for this. Well, before I even talk about that, so that's what Prim's algorithm is. What could Prim's algorithm be used for? Give me an example of something you wrote down. Go ahead.
Generating a maze.
Generating a maze. Okay, tell me how it could be used to generate a maze. So I know that's one of the examples, but so how is what we just talked about something that could generate a maze?
It'd start at a random entrance point, and the last node it connected to could be the exit point, and it just generate a bunch of different paths going from the least weighted value to each place. And then
so with that in mind, wouldn't you have a maze already? How does a maze actually get generated? You want to create maze entrance and maze exit, and then you have all these other dudes in there. How do you how do you actually create that maze? How do you use Prim's algorithm to generate it?
by using the connections between each point.
Well, so if this is the entry point, I can go left, I could go at a 45-degree angle, or I could go up. That maybe is the maze entry point, right? So I can either draw a line up, draw a line across, draw a line over here. But don't these lines already exist? Okay, but we know we want to exit here in Sheboygan, if you will. So that's our maze exit. Now, to successfully complete this maze, we have to ultimately get to Grafton, which then that's the one path that leads us to Sheboygan. But there's multiple ways for us to get to Grafton, right? There's actually a whole bunch of ways we can get to Grafton. We can go Mequon to Grafton. We can go Mequon to Cedarburg to Germantown, back to Mequon up to Grafton, so on and so forth. So we can circle back on stuff. So when you say it's used to generate a maze, is it used to generate or could it be used to solve a maze? Okay, so clearly it can be used to solve. But I think the example mentions that it can be used to generate a maze. How? How could a maze actually be generated from Prim's algorithm? Let's think about the problem of creating a maze. So, we're going to have a piece of paper sitting in front of us. We're going to put a little dot where we're going to start, put a little dot where we're going to end. And, we might decide we're going to draw, a bunch of lines, and then we'll draw little pathways around the thing. Can Prim's algorithm generate those hallways, if you will, the place that we need to go? Can it decide on those edges without actually taking the edges? Think about how Prim's algorithm works. We just described it. We've described a specific use of it where it takes every single path that leads from a particular node. But if we think about that, let's think about like we start in Mequon. Now we need to split ourselves into 3 pieces, right? Potentially. We need to go this route, and this route in terms of traversing a tree. Now, if we know these weights ahead of time, Prim's algorithm would say we'll take 8, right? And we get here. Well, then what's the next thing that happens with Prim's algorithm? It says we're going to take 5. Okay, then what's the next thing that happens with Prim's algorithm? It says we're going to take 10. And then what's the next thing? It says we're going to take 16, but now we're back to something we've already visited.
I thought Prim's algorithm in between 2 nodes that have already been used doesn't look at that connection anymore.
It's true.
The value.
It's
so
true.
When it'd go 8, 5, 10, and then 28 from Grafton is Sheboygan. Because it wouldn't look at 16 because Germantown was already used and Mequon was already used.
Right, but the only place we can get, with Prim's algorithm, we'd be stuck in Germantown.
Okay.
We followed we can't go to Mequon, we've been there. So this is a dead end. So what does Prim's algorithm do? You said it ignores paths we've already taken, right? Well, so taking this path led us down a bad path. Goes back where? Okay, well, so if we decide we're stuck here, we can back up 1. Are we stuck here? Go ahead.
So if you consider the maze field as a grid of nodes,
Mm-hmm.
then it would, since each node there on there is essentially equally distant from the one it starts at,
Mm-hmm.
then it would just take a random path to one of the 4 adjacent squares, and then keep doing that until then, if it realizes that there's no option because it took those nodes already, like
Mhm.
it runs into a dead end, then it would just stop and then continue on at the other locations until the whole grid is filled up.
Okay, filled up with like partial pathways. Okay. With that in mind, is there a guarantee that there is a pathway that does lead to the end? So you want to create a grid of, so, if we were going to finish filling this out,
Yeah, because
we can do
then
this.
at least one of the searches won't die until the end.
At least one of the searches won't die until the end. All right, so if this is begin, each one of these is our grid. We want to get from here to here. And you want to start the algorithm at each one of these points. And then have it randomly, and you're saying each one of these weights is equidistant, right? So this guy is 5, this guy is 5, this guy is 5, this guy is 5. And maybe usually mazes are just 90 degrees, right? So we probably wouldn't have these diagonals. So maybe we would take that out. So we would have connections between all of these individual guys like this. And they would all be 5. Okay, so at that point, it would be like tie goes to the runner, so you would just randomly pick one of the roads because they're all equally good. So if we started here in Mequon and all these guys were 5, so on and so forth, and draw it up there farther. So if we start here, we're going to pick either one of these two roads, right? And basically draw up a hallway, a road between Mequon and Grafton in this particular thing, okay? So after I do that, then what? Randomly pick another?
Right, but you have to remember, since, or, well, because if you're working with the same phase, then you have to be remembering the last, every time you come to an intersection.
Your choices of random paths can't be places you've already traveled. Okay, so the second we take this route right here, this edge has been drawn. We've drawn that edge of the maze. So now we're sitting here, we only have two edges to roll the dice between, right? All right, so let's say we take this edge. All right, so we now have taken that guy off we've drawn that hallway between those two. All right, so now we're at our end point. So we're going to say we're done?
That one's done, but then you go back to Mequon because there was more options in Mequon.
Okay, so we'll go back to Mequon, and now we're going to randomly roll the dice of the edges that are left, which is just this guy. So we'll take that. And now we're going to randomly roll the dice of the edges that are left, which is this. Then we're going to randomly roll the dice of the edges that are left, which is here or here. So let's say we go, let's say we pick this guy. Okay, then we pick this guy, then we pick this guy. We can go here, from here to here. This pathway hasn't been created yet. Or you don't want to visit. Okay. You want to omit this by the normal algorithm. Okay, so you're going to say there's only one way to get to Sheboygan. Fair enough. Okay, so basically we would get this. So we have that. We have that. And we have that, except this guy never gets drawn, right? So at this point, we've drawn this and this. We have, let's get these out. We've drawn this. We've drawn this. We've drawn this, and we've drawn this. Okay? Now what?
Well, I don't know what order it would be, but then.
We're done with Mequon?
Right.
Okay, we're done with Mequon. So now we're going to go to another one of our starting nodes.
It would either be the left Cedarburg in the middle or the Graph.
Doesn't matter? Or have we
Well, it would matter. I just don't know how the algorithm would
okay.
remember.
Well, doesn't Prim's algorithm say if our goal is to make sure we visit all these places at least once, then wouldn't it say that we will go ahead and try from every starting point? I mean, that's what Prim's algorithm says. We're searching for the minimum spanning tree that visits all of these guys, but we need to, in order to find the minimum tree, we're effectively trying to find what's our best starting city. So we're kind of halfway talking about the traveling salesman problem right now too. So if we don't have a limitation on where our starting city is, any one of these guys are fair game. When we start talking about generating a maze, we have a little bit more information. We know what our ending city is, and we know what our starting city must be, right? But that doesn't mean that we're not going to hit other cities that have roads that go out from them. So if we just treat Mequon as our one starting city, we get a maze that looks like this, because we've hit every single path that leads out from here. So what if we pick this guy as a next potential starting point? Because this is a point that we currently go through, right? So maybe when we were drawing this, when we went from Mequon to Grafton, since all roads were equal, rather than picking one, maybe we picked all. So I drew in that. Could I have at the same time maybe spawned off a thread or just made a recursive call that says, let's go this route too. So we'll follow that path. So we tried both of these directions. Just like at the beginning here, we tried both of these directions. So both of these directions led to here. Both of these directions led to here and here. From here, we can try this direction. We can also go this direction. Something like that. So we had our one starting city, but every time we visited a node, since there was a tie, we took all of those roads. One road wasn't necessarily better than the other, so a greedy algorithm would say, let's visit all. So we can think about it as multi-threading, or we can just do a recursive where we'll try to visit this one, and as soon as we've gone down that path, we'll then visit this one and go down that path as far as we can go. Go ahead.
All right, but if it takes into account all starting points, this wouldn't be a minimum spanning tree.
Well, if it takes into account all starting points, but for a maze, we would limit it and say we only have one starting point.
All right.
Okay, so if this guy is our one starting point, and this is our destination city, at this point, the traveling salesman problem would say that you're a traveling salesman, you have your start city. Well, there's probably two versions of it. It might say you have your one start city at your home, and you need to visit all of the cities on your route. What's the most efficient way to drive? You know, what order do you visit the cities in so that you only visit them once, but you visit all of them?
You have to make it all the way back to your hometown too, because that would be part of the problem.
It would be.
You'd have to calculate.
Yeah, for the traveling salesman problem. Yeah.
Isn't the traveling salesman problem, wouldn't that be dealing with, well, I guess you start out undirected, but like the actual problem, like the salesman, you have to take into account the direction that he's traveling in. So like, if you say Sheboygan wasn't the ending point,
Mm-hmm.
and it happened to be in Grafton, and then the salesman goes to Sheboygan, and then they have to come back to Grafton to get somewhere else.
That would be off limits.
Right. Yeah, because like in this minimum spanning tree, wouldn't that, like, you're not penalized for coming back from Sheboygan.
Right. Traveling salesman problem officially says that you can't visit any city more than once. So if you've been in Grafton, you can't come back to Grafton. Unless, if that was your home, that would be your final return. Go ahead.
And if we ended in the upper left Cedarburg and needed to get back to Mequon, you couldn't just take a direct route back.
Not if there weren't roads that went direct route. You could follow a minimum spanning tree that starts at Cedarburg back to Grafton. So you would look at all spanning trees that start at Cedarburg and end, or have a subtree that has Grafton in it, and follow that.
So basically, you'd have to make sure you didn't go back over them. So, well, I guess that would have to be the minimum spanning tree.
Well, sure. Well, so pausing that for a second, is this a maze? It's a small maze, but is it a maze? Okay. Well, I mean, we would add more points, right?
Yeah.
But does that effectively create a maze for us? We started at our starting point here, and we said, let's use the minimum spanning tree. Let's use Prim's algorithm to visit every possible, in a greedy way, every possible way. It just so happened that all of our roads were the same length, which causes Prim's algorithm to say, well, let's check all of them. Let's go to this road that's 5 miles long and this road that's 5 miles long. We'll split ourselves and go both of those directions, because we're ultimately looking for what's the best, and we don't care how long it takes, right? And instead of searching for whether we visited everything, we're using the nature of the algorithm to effectively drill these particular pathways between our visiting cities or points in our maze. that kind of make sense? Okay, so the greediness of Prim's algorithm says that we're not going to care about speed. Instead, we care about visiting every possible way this can happen. And in the end, we're going to determine a path of least resistance, the one that had the shortest total goal. So could we then go back and say, well, I guess this wouldn't be Prim's algorithm anymore, but could we effectively determine minimum spanning tree from the start point to this end point? So every single spanning tree that starts here and ends here, and find the minimum one, and that gives us the best pathway through this maze. So in that particular case, we would generate a spanning tree that goes from here to here. Okay. Now technically, it's not a full spanning tree because it doesn't visit every node. In our case, the definition of that tree would be one that starts here and ends here, doesn't necessarily visit everything else. All right. So I don't think it's unfair to call it a spanning tree, but it doesn't meet the requirements of visiting every single node. So that would be one option, has a weight of 10. Another option would be 5, 10, 15, 20, 25. Another one would be 5, 10, 15, 20, 25, 30, 35. And does that cover all of them? I think that covers all of them without having loops. Those are the three ways we could go through this maze without visiting the same city more than once. Say this again?
You wouldn't be touching every city?
Well, that particular one we did. We took the scenic route. The last one. We went Mequon to here, to Cedarburg again, to Cedarburg again, to Cedarburg. Yeah, and then up to here. So in that particular case, we did visit. That would be a true spanning tree that visits every single node in our tree. Whereas this guy that gets us to our ultimate goal, Mequon to Grafton to Sheboygan, only had a weight of 10. That would be the, that's probably like the maze that's on the Red Lobster menu for the kids. Just straight line, then you go and you start making the little crab guy with the paper. I love making those. So in any case, that wouldn't truly be a spanning tree, but it would be a way of traversing this this maze. So with that in mind, could we use I mean, at that point, it's not Prim's algorithm, but it's similar to how Prim's algorithm works. It would be a greedy algorithm type of approach to visit every single to find your way through a maze in the quickest possible way, by effectively every single time you hit a fork in the road, if you will, you split yourself up and go down each path. And then the worst case is you meet yourself at the end. So up here we have three of ourselves that all come back together, and we ask each other, how far did you travel? And one guy says, well, I traveled 10. Another guy says, I traveled 25. Another guy says, I traveled 35. And then the guy who traveled 10 knocks the other two out and says, okay, the quickest path here was 10. Does that make sense? So now, interesting question. What about GPS? Think about applying this to GPS. So when you type into Google Maps that you want to travel from Milwaukee to Las Vegas by car, how many roads exist between here and Las Vegas that we possibly could take? A lot. All right. So do you think that your GPS there is in real time doing a kind of a total search, starting at Grafton or starting at Milwaukee and visiting every single road leaving Milwaukee, period, looking at all the ones that lead out to Las Vegas, even the ones that head east first, almost like air travel, right? You fly to Atlanta to get to Las Vegas. Okay, that kind of stuff. Do you think that your GPS on your phone does all that work? Or is it probably leveraging some pre-homework that Google's probably done and said, this is where I'm ultimately going, throw out a whole bunch of options? Okay.
Doesn't it have wouldn't wouldn't all be based on distance, though. It would be based on like distance times the speed you can travel on that road.
Well, isn't that a different weight?
Yeah.
So instead of distance, you might say distance per speed, or time, which is distance relative to speed.
You'd also have to factor in like stoplights, because like you wouldn't be able to tell that, because that could be at one of the intersections, whereas another one could go straight through. Like, say I'm going from German down to Milan.
Yep.
It's gonna be like
Lots of stoplights
say
there.
that's 10. Oh no, I'm saying there's no stoplights. 'Cause we're not stopping anywhere in between.
Right now we are, but in reality, if we went from Mequon to Germantown, there's stoplights.
But okay. But say each one of these is an intersection. So going from the bottom left Germantown to Mequon would be 10. Let's say. And going from the Cedarburg to Grafton in the middle, that's also 10. But you'd have to calculate that stop in between could take longer, because the Cedarburg in the very middle would be an intersection. So you'd also have to base it on like how many turns you have to take, even though that might not take longer. That could slow you down, so you're going to stop.
You probably, if you think about how your GPSs work, what it typically does, and this, now they can take in more information now with real-time traffic, right? So what they're doing is they're adjusting their edges, the weights between places, based on the current average time it takes to traverse an edge. Okay, and that is speed of cars, current traffic, the last cars that have gone through here. I think Google uses some satellite stuff and also brings in information from a bunch of different sources to try to keep its. If you've ever been using a GPS and it gives you an update, there's now a route that's 3 minutes faster or something like that, and it reroutes you. Okay, so that's doing some real-time updates depending on where you currently are in your map. So as you've already traversed, your starting city is no longer the old starting city. It's having to do this search again. Punchline here is that GPS instructions are related to what we're talking about here. But your phone, your Android phone or your iPhone, isn't doing. It's not checking every single possible path that you might ever visit.
If you go through like Texas to Vegas.
Well, not only that, but the number of things it would have to check would be astronomical, and it would take 6 months to if you're going to downtown Milwaukee to some restaurant you haven't been before, and you punch in the coordinates, you need to be there in a half hour. You don't want it to take any longer than probably 20 or 30 seconds for it to figure out the best route. And in 6 months, it's going to tell you how to get to Buka. That's when it finally finishes traversing the whole country.
Couldn't you like set?
It's gone into Canada a little bit too.
You're gonna tell it, I don't want to go so if we're going from here to Vegas or whatever, you're gonna set perimeters, because there's no knowing ahead of time, you wouldn't want to go too far this way or that way. And so
Yeah, but that's not one of the settings in your GPS. You don't get to say, I don't want to go west to go east. You get to say, I want to avoid toll roads and things like that. So that's going to take some edges off the table as being illegal edges.
I'm saying just do that ahead of time, like the GPS would do that in its programming, because it's like using any of these roads is obviously not going to be faster if it's not.
Why obviously?
Well,
what if it's faster to go east to get west because all the roads west immediately out of town are closed? And you actually have to go east, then north, then go west. So obviously, is it really a thing?
Well, I'm just saying, like, if you set up a big enough parameters and you set, like, you could, since you're driving, you're going to leave your GPS on.
Mm-hmm.
It needs to tell you directions. It could, like, seeing that it's a long distance, could set somewhere that's, like, halfway through. And then, as you're going, keep recalculating and keep moving the point further and further.
See, this is a great example because you're thinking like a human. And that's not how computers work. You would be intelligent enough to look at a map and say, okay, well, if you had an active map that kind of, had red lines where there's bad traffic and stuff like that. So if you go on to one of the traffic sites and it kind of shows you that live map of where the traffic is, you could at a glance kind of figure out what might be the best, relative route to take to Brookfield from here based on where it looks bad. Like, I'm not going to go on 94. I'm not going to go on 94 West because 94 West is basically, a parking lot. So I'm going to stay north here and dribble my way to the west and then head south from there. As a human being, you could look at a map and bring in all this information fairly quickly because human beings are good at that. But now you have a computer program that has a zillion variables it has to take into consideration. And how do we fish through those so that it doesn't take 6 months to find our destination? As a human being, you're going to say, obviously, I'm not going through Atlanta to get to Brookfield.
But couldn't you okay, so say we started here and we're going there. You could, instead of just starting at some random point, you could be start at the point closest to a line going directly. I think it's start your calculations based on whichever one's closest to that line and then work your way out. Going that way, and then stop at a certain point because you're not.
Okay, but that still assumes that line is the best line. There might be an arc that actually is faster.
That way to go to the highway rather than go.
Stuff like that. The number of parameters that are actually being taken into account. Because when your GPS gives you directions to a place, you can put in, do you want it to be shortest distance, shortest time, that kind of stuff, avoid toll roads, some big picture stuff like that. Even avoid interstates if you're, taking you're pulling a big trailer or something like that. You might. Yeah. How do I off the grid? That would actually be a funny April Fool's update to Google Maps for GPS instructions. You have a choice for just off the grid. It's taking you. It takes you through farmland, literally farmland, not roads. It's giving you an option for horseback. That would actually be really funny. That would be a good hackathon project. Modifying, writing a modified GPS thing that overlays on a map that avoids roads, purposely avoids roads, and it gives horseback instructions to a destination.
You could take your horse up and over a house. You really because you're saying you'd go direct, because otherwise you wouldn't know
Well, you'd have to look at the topography maps, and take you'd have to be able to identify houses when you're looking at. The satellite maps rather.
Density, then you gotta change your direction.
You're up there presenting on it, talking about best route by horseback, and how we actually use a series of lasers that we attach to a helmet that's on Google's stable of horses that they use to just normal Google Street View. They have to send the trucks all over the place. We're going to send horses out to we lost 4 horses today because
Well, that's the hackathon we went to. We went up there and just showed that, and all you did was say that. And
it was a particularly great watering hole in the prairie land. And the horses stopped to take a drink.
Yeah, you have to walk past X amount of rivers every mile because you don't want
your horses have to be able to drink. That would be a pretty funny Google, April Fool's release. Visit America by horseback. What's this?
Except for people who would actually have to get somewhere and then accidentally click that.
Actually, the sadder thing is there's probably a small percentage of Americans that would really benefit from that app. Man, I've been looking away at how to get to. I wonder if people do that. Do people actually caravan via horseback, Oregon Trail type thing, as I don't know, historic type vacation reenactment type stuff? Yeah.
You know how bad for your back that would be to ride?
Well, no, I'm not sure you're qualified to answer this, given your. It's I don't like mosquitoes, so.
Well, even in Alaska, The Last Frontier, I don't know if you've ever seen that show, but they use ATVs, so I don't even think
it's the same as a horse. You got to put gas in an ATV. You got to put water and food in a horse.
Walk across some gas stream, fill up your tank.
That's right. Horses are going to be more, they're going to be more flexible. You could take your ATV to certain places, but you're going to run out of gas eventually.
That's why we need this.
Horse, you just follow the water. Follow the rivers. Plus, there's fish in there. Bring your fishing rods with you. Or you can maybe just have a trailer with a bear in it. train the bear a little bit so it won't kill you, but send it in the water for it to catch some fish, and you
We're
just
gonna eat the fish first. It's not
yeah,
gonna be
you
like,
share with
"Oh,
the
I got
bear.
a fish. I'm not gonna eat this. Here you go. You had me in a cage all day. Why don't you have it?
In the cage all day. All right, so we'll understand the basic principle of Prim's algorithm and kind of the problem it's trying to solve. All right, so what we're going to do is we're going to actually explore this not directly through Prim's algorithm. Prim's algorithm is pretty specific, and we've kind of looked at that today when we've said that, technically this isn't a minimum spanning tree. It is a shortest path between two places. Prim's algorithm kind of leads us down a path that says, what is the most efficient way to visit all nodes on a tree? All nodes in a graph is the more appropriate way of saying it, given no restriction on starting point. That's what Prim's algorithm says. I can pick any of these, well, I'm going to pick all of these starting points, and I'm going to fully explore the graph. And then I'm going to compare all of my spanning trees that visit every single, well, by definition, they visit every single node on the graph, and decide which one is the minimum. And that's going to give me two pieces of information. It's going to say, where's my starting location, and how far will I have to totally drive, let's say, to visit everything. All right, so that gives us a very specific type problem that allows us to solve, which then takes us back to this traveling salesman problem, which says, what is the best order to visit all cities on a route such that we only visit each city once while minimizing our total travel distance, whatever that means. Okay? So that's the premise for a traveling salesman problem. We've understood Prim's algorithm as being, kind of a potential approach to that kind of problem. But what I wanted us to get out of this conversation is just the generalistic idea of a greedy algorithm and traversing a graph. So to even start thinking about that, we need to consider, how do we build a graph data structure? We can't even start thinking about traversing one until we have one, right? Okay, so what's the difference between a graph and a tree? How would you build one of these graphs? What kind of information do you need to build a graph?
For like this one, you need all of it. You need to know.
Well, what's involved? What's involved in a graph? When we're talking about cities here. So we need a list of cities, right?
Yeah.
That's the starting point. What are the nodes in our graph? So if we're building a graph, let's actually insert a guy here. So a graph, we'll keep it specific to traveling salesman right now. So it kind of leads us down our homework. So we're going to say graph of cities for traveling salesman. So we're going to need a list of all cities. That's one thing we're going to need. So these will be the nodes in our graph. Okay? So for us, we're probably going to have a text box that allows us to add cities. All right? Text box that adds cities. So we're going to need a list of all cities. You could also just, if you wanted to, just have a comma delimited list of cities and split it. It doesn't matter to me how you pull this off. Our initial goal is build a graph of cities. Okay, so list of all cities, these will be the nodes in our graph. Secondarily, what are we going to need? We're going to need a list of all edges. And what's an edge? An edge is a link between two cities with a corresponding distance. List of all edges. These will be, this will require three things.
Is the list of edges that would be attached to each individual
No, usually building a graph, they're separate. So when we think about what pieces you need to build it, you kind of put all your puzzle pieces out here. Then you open the package that has all your edges, and it says, okay, well, this edge goes between these two guys. This edge goes between these two guys. So you'd have to search for your two nodes and then throw that edge between them. Kind of make sense how that works?
So it would require start and then like the distance between.
That's it.
Are the three
Yep.
Okay.
So that's fine. We'll call this city 1, city 2, and we'll call this distance. So you can make this more generic for a generic graph. We're kind of building this specifically for traveling salesmen. So we have a list of all the cities that are on our map in our graph. We have a list of all the edges that connect whatever connects. You know, every city doesn't necessarily connect to every other city. All right. So with these two things, we would then be able to build our graph. All right. So let's say that then produced for us. Let me steal this entire thing. I'll go down here. We'll paste this in here. And let's take out some of this extraneous stuff. Sheboygan, Grafton. I think, didn't this guy connect here? And then I think we had this connection before. All right, so in this example, we would have a list of Mequon, Germantown, Cedarburg, Grafton, and Sheboygan, listing all of our nodes. Then we would have a list of this edge, which would be, that's what we have that at 8. So Mequon would be city 1, Grafton would be city 2, 8 would be the distance. Then we would have, 15 is good enough, Mequon, Germantown, 15, that's the distance. Mequon, Cedarburg, say that was 10. Germantown, Cedarburg, let's say that was 9. Cedarburg, Grafton, let's say that was 7. And then Grafton, Sheboygan, let's say it was 28. Okay, so you'd have defined each of these edges. So then to build that graph, you'd have to go through searching through all of your nodes. So you've effectively created a list of nodes. Now you don't know how many nodes you're going to have. So when I provide you, when you provide yourself, I suppose, a list containing all the cities, and you need to build node objects out of that list, how many cities will there be? You don't necessarily know, right? Now when you split it on a comma or something like that, then that'll give you an array of cities, so you will know how many you have. So you wouldn't have to build this out of a linked list. But if you wanted your graph to have things added to it in the future, you probably want to store your city nodes as a linked list so that you can have more cities in the future. All right? So that would be the starting point. So you're going to end up building a linked list of all the cities as nodes. And then a node, so if we think about the nature of a node for a graph, we'll call this a graph node. A graph node has a city name, in our case, and a list of edges, okay? Where an edge has a weight and a destination. So when you have this edge, the edge between Mequon and Germantown, Mequon will have an edge that has a weight of 15 and a destination of Germantown. Germantown would have an edge that has a weight of 15 with a destination of Mequon. That make sense? All right, so your homework assignment for Tuesday is going to be to, I don't care what kind of interface you build to do this, but effectively create a graph data structure given a list of cities and a list of edges. Produce that data structure. And then you're probably going to want to maybe go through all your cities and print out the stuff just to prove that you've generated all the edges. That makes sense? All right. Questions about that?
So, like with that one,
Mhm.
this is just the base one, but with the graph that we were just at, this would be impossible to do in the Salesman thing. Because you couldn't get to Sheboygan and back without crossing through the city.
Right, I guess technically yes, but that doesn't necessarily matter for this homework assignment. Yeah, but the idea is you would visit every city and then have to come home.
Yeah.
So, I mean, you could
So
break
like,
that
on your
rule.
way back home, you can pass through a city.
Yeah, it might be a necessary evil, just because of the nature of our map here. Okay, lots of closed roads. Plus, this is all horseback, of course.
Or is that a peninsula and there's only one road?
Yeah, this is over the. Yeah, it's over the water.
Yeah. So you need like your hoverboat to get there. But
That's right.
the road down, that's-
All right, so homework: create a graph and prove that the graph was created. All right, you don't have to traverse it or anything. Just create the initial data structure. I will see everybody on Tuesday.